Hello, it's Keith here, and this is lesson 2 of my platform-specific Z80 tutorials. In this series of tutorials, we're going to be learning about the hardware itself and how to make it do the things we need for the multi-platform series. So today we're going to look at extending the code we did last week, because last time in lesson 1, the keyboard reading code wasn't great on the Ti-83. It was reading weird symbols, and on the Spectrum also it was coming up with the control codes that the keys return. Also this week, you'll notice we're now up to 6 systems because we're going to start learning about the Sam Coupe. So the multi-platform series is now going to be covering 6 different systems. So let's make a start and let's have a look at what we're going to be doing. So just to demonstrate what we're going to be programming this week, I've written this little program here. It's very simple. All it does is it moves the cursor to the top corner of the screen at position 0, 0. And it uses this new function called GetCursorPos. And what GetCursorPos does is it reads the current position of the text cursor and it returns it in the same format as our locate command. So the X coordinate is in H and the Y coordinate is in L. Now, last week in the multi-platform series, we wrote a function called pushRegister, which allowed us to quickly see on screen a register pair. And so we're running our GetCursorPos. That returns our HL location and then we show it on screen. And so if you look at the Amstrad CPC example here, you'll see in the top left-hand corner, you've got 0, 0 shown, which is, if you think of the cursor position as the first star before the hexadecimal pair there. So the first one is 0, 0, and then the next one is 6 characters across. So that's 6, 0, that's 6 across, 0 down. And then the next one is C0. And then on the next line, we're 1 line down now. So we're at 0, 1, and then 6, 1, and then so on. And if you have a look at the Ti-83 calculator, which has grown itself to enormous proportions for some reason, you'll see that because there has been a sort of carriage return force by the screen here, rather than 0, 1, this one shows 0, 2. So it is actually reading the location of the text cursor on all of the systems. And we're going to need this for a later lesson. So that's the first thing we're going to be doing. And also we're going to be defining some definitions that we'll want later. We're going to be defining the keys for the enter key and the delete key because they do differ depending on the systems. And also we'll be defining the screen size because again we might need to do things later slightly differently depending on the screen size. So we'll be making those definitions. We'll be defining the new GetCursorPos command and we'll be fixing the Spectrum and the Ti-83 versions so that they read in proper keys. Okay, well, we're going to be creating some definitions this week and we're going to be creating them in the header files here. So the header files in my programming scripts appear at the start of the program immediately after the org definition. And there's a very important reason that we're going to do this, and I'm going to show you about it now so that it doesn't cause you the kind of problems that it caused me. Now, this may well be only the WinApe assembler. Other assemblers may not have this problem, but it does seem to be a quite significant problem when you're using definitions and when you're using IFDEF commands to have branches of code that are only compiled depending on the definitions. So let's have a look at this program here. We'll just reset our Amstrad CPC here and let's have a look at this program. So you'll see the program starts with a jump to test B, and test B is here. We've got test C, which won't really do anything, and then we've got this symbol here called use test A, which we're defining to 1. Now if use test A is defined, this extra chunk of code is compiled here. So let's just rem out use test A and assemble here. Okay, so you can see we've got a jump to test B. The use test A block isn't compiled, and then we jump to test B. Okay, so let's just do call and 8000, and it shows a B because this has been executed. The call jumps to here, and it prints the B to the screen. Well, that all makes perfect sense. So what's going to happen if I re-enable this definition here and this section is compiled? Now logically we would probably think, well, the jump is going to go to test B is down here, so this will be compiled into the code, but it'll never get run because we don't ever call to test A, and this is a jump, so there's no return. So yeah, that makes sense. Let's just quickly compile that and let's see if we're correct. So we've called 8000, but it's actually run test A, even though there's no path of execution that should end up with test A being executed. Now what went wrong? Let's have a look at the assembly. Okay, so here's our test A, which is now being compiled because that definition here is true. And here's our jump to test B. Now if you look, the jump to test B is at 8003, but test B isn't at 8003, it's at 8008. And what went wrong is the way the assembler works is it processes the code twice. And so the first time it goes through, and when it gets to here, it thinks, oh, well, test A isn't defined, so I won't compile this. And then it says, oh, well, test B is the first thing after this jump block, so 8003. But then when it gets to the bottom here, test A is defined. And the second time it goes through the code, this is then compiled. So the label test B ends up, the jumps to test B are no longer in the point that test B occurs. This seems to be a limitation with WinApe. I think some assemblers may not have this problem. They may do a third pass, but it's definitely a problem with WinApe. And the solution's very simple. You just need to make sure your definitions occur before the first IFDEF command that uses them. And that's why the examples today, we're putting all of our definitions in the header, because that makes sure this cannot happen. So if I just assemble this again, now that test A, the definition of test A is at the top, and if we do call and 8000 now, you'll see it shows a B, which is exactly what we'd expect it to do. So it's kind of a malfunction of WinApe because our definition was after the IFDEF statement. So just to make it simple, don't use IFDEFs, and make sure your definitions that are used by IFDEFs are at the start of your code. So there we go, and that's what we're doing today. So if we just have a look at the CPC header here, you'll see we're defining a few functions here. We're defining keychar enter, which is the symbol returned by our waitchar command for the enter key. We're defining the backspace key. And then we're defining a couple of variables for screen height. One we're just defining in this way, which is just a true or false kind of statement. And the other we're defining as a number. And the reason we're doing this is the IFDEF command can be used to, if we need a next section of code to compile only on 40 character wide screens, we could do this. But if we wanted to compare, if we wanted to sort of load A comma B to see if B is over the screen width, then we would do it like this. So that's why we're defining it twice. Now, unfortunately, as far as I can tell, WinApe, while it can do simple if definitions, it can only, an if definition of this kind will only compile if the value is greater than 0. You can't create a definition that does something like this, as far as I can tell. If anyone can figure it out, please let me know, because I've looked through the help files. I can't find a way of doing it. But I really wanted an if GT or greater than or something like that, but it doesn't seem to be possible. So that's why I'm defining these in two different ways. It's for different kinds of compiler directive. So that's the definitions we're doing, and we're going to be doing those on all of the systems. Okay, so let's start with our CPC and have a look at the new command, which is the GetCursorPos command. So here it is, and on the Amstrad CPC we're just using a function called to text GetCursorPos, and we decrease H and L because our locate command starts from the top corner 0, 0, but the CPC returns as 1, 1. So we just decrease both to make it match our expectations. And that's all we need to do for the CPC. Now, let's just go back to my example here and recompile it, because there is one other thing I need to probably show you about this example. So if we just do a CLS, you call and 8000 to start it up. So after it's shown the text cursor positions, we can then just type away. So if we type hello, it will do that. And then you'll notice we've put in these checks for the newly defined characters, so that if we press enter, we can start a new line. And also we can press the backspace key to clear the screen. So just a few little, just playing around a little bit there. So we've just added a few tests for keys there. Okay, so that's all we need to know about for the CPC. So let's close that. Now let's have a look at the Enterprise. The Enterprise is actually a little bit interesting. So on the Enterprise today, all we need to do is create a definition for our GetCursorPos command, but you'll see it's quite long. Now the reason for this is there isn't a function call within the operating system to get the current cursor position, and what we do is we actually poll the screen we send the screen another escape code combination, and we send it the character that's known as escape, which is hexadecimal 1B. Then we send a question mark, and the screen will then wait with the information we want. And to get that information, we actually open to a read channel to the screen and read in 2 bytes. And then to get the 00 reference to values we want, we have to subtract hexadecimal 21, because the enterprise screen starts from 1,1 and it adds hexadecimal 20, 32 to the values by default. That's just the way it works. So as I say, we're looking to give common values back from all these functions so that we can use them for the multi-platform lessons later. So, but yes, so we send this block of commands here. The screen then becomes ready with its data. So we open a read stream here. We read in a byte, and then we read in another byte, and then that's it. It's a bit odd, but it's perfectly functional, works very nicely. And there we go for the enterprise. Now, the Ti is even easier, would you believe? Here it is. It's so easy I couldn't find it. So the Ti-83 by default stores its information in 2 bytes of memory, and they're actually in the perfect format we want. So we just load them straight into HL and then we're finished. So that's it. But of course, with the Ti-83, we do have some more stuff we need to look at. Now, I don't know if you remember last week, but the Ti-83 last time was causing us some character problems. When we pressed the keys, it was coming up with weird symbols, and none of the keys on the keyboard were returning anything that we could really make any sense of. Now, this week I've put in a few little checks here, and I'm transposing the 0 to 9 range and the A to Z range so that we can get normal number keys and normal letters out of the system. And so now you'll see if we press 0 and we press 9, we're getting numbers out of these keys here. And then if I press the shift and the alpha key to turn on alpha lock, I can press the F key and I get an F. I can press the U key and I get a U. And there we go. And of course, just like the other systems, I've mapped the enter key to the new line, and I've mapped the delete key to clear the screen. So thanks to this little bit of code here, I'm now getting the basic A to Z and 1 to 9 working in a way that we can use for our common coding. Of course, we could go even further and convert the entire character set, maybe with a lookup table, but I thought that'd be quite wasteful for memory. So I'm just using this very basic one so we can get letters and numbers, and I think that'll do enough for us in these early days. So on the MSX here, we've got our GetCursorPos command. Now again, almost as easy as the Ti-83. We just load it in from this memory location here, but again, it's 1,1 based. We want 0,0 based, so we just have to decrease H and L and then return back to our program just to get the values that match the other systems. But again, very easy on the MSX, and there were no other problems that we were fixing this week on the MSX. Now onto the ZX Spectrum. GetCursorPos is a little bit weird. We can read in from 2 memory locations, but whereas when we were defining the cursor location, we were defining it from the top left, it seems when we read it back, it returns it from the bottom right. So we're actually having to do a subtract command to flip the cursor location around so that it matches the one that our other systems are using. But this rather strange little function here does actually return the kind of locations that our locate command uses and that our other programs are using. So that will do the job for us here. Now, last week there was quite a problem with the wait char command. It was returning the weird control codes from the keys that give the basic commands, and obviously that's not going to be very useful to us. So I've actually completely swapped out that for a completely different function this week. The one we're using now is actually processed by the firmware interrupt handler. The firmware interrupt handler will read the keyboard and store the correct ASCII key for the pressed key on the keyboard. And so all we're doing is we're setting this location 5C08 to 0 so that we're waiting for the next key to be pressed. We're then reading in the key. If it's not 0, because then the interrupt handler can't have happened yet, so we wait again and wait for a key to be pressed. Now, unfortunately, that works fine from the point of view of reading a keyboard, but We do have the problem that some of our code might be disabling the interrupt handler. Because we're now relying on the interrupt handler to read the keys for us, we need to make sure it's enabled. And so what we're doing here is we're doing the same trick as we learned last week in the multi-platform monitor, debugger monitor, and that is when we load the I register into the accumulator, the Z80 will rather surprisingly set the PO flag if interrupts were disabled. Now, we're just doing a push of the flags here, pulling them back, and then we enable interrupts here, but then if the PO flag is set here, then they were disabled before this point. So we're just calling this disable interrupts function here, which will disable interrupts in return. So this will, if required, will disable interrupts again once our reading of the keys has worked. And the net result of all of this is the interrupts are enabled for this point, for this reading of the characters, so that this doesn't cause an infinite loop. But then when our program execution returns to wherever it was, interrupts will be at the same state as they were before this was called. So that's a bit of a workaround. As I've said before, I'm not particularly happy with using the firmware functions in this way, but we will work on some functions later that don't use the firmware at all for this kind of thing. But for now, I want to use the simplest way of possible of getting basic text reading and writing working on all of these systems, so we can start writing some interesting programs using them, and we'll worry about making better functions for this once we're feeling a bit more confident with the systems. So that's the new wait character function for the Spectrum. Okay. Which brings me on to the new system then. So thanks to a YouTube suggestion in one of the comments, I'm now looking at the SamCoupe system. I will do a separate video for the SamCoupe and describe it in more detail like I did with the Enterprise, but the long and the short of it is, from the point of view of what we're using it for now, it's perfectly functional and it worked very nicely for us. So as you can see, we've got the same cursor locations, we've got the same ability to write text to the screen and to clear the screen. So let's have a look at all of the functions we've defined for the SamCoupe to get us working today. So print character works very much like the Spectrum did, really. We've got an RST function here which will just send the character straight to the screen. Now we're having to protect an awful lot of registers here because it seems the SamCoupe firmware does change quite a lot of them. So this will make sure that everything works fine, and that will just print our characters to the screen. Now our wait character function, I was actually having some trouble with one of the firmware functions. There was a firmware function that I thought would do this more easily, but it didn't seem to work for me, so I've ended up using this read key one here, and that actually returns immediately if a key wasn't pressed. So that's caused a little bit of extra confusion. So what I'm doing here is I'm looping around, because this JRead key firmware function will actually return 0 if no keys were pressed. So I'm using that to loop here indefinitely until a key is pressed. But then this will return extremely quickly, and so we need to do a pause to make sure we don't return hundreds and hundreds of key presses that were actually all the same key press. Now one option would be to enable interrupts and do a halt, but as I've said before, I don't really want to be using the firmware functions like that because we don't know what that interrupt handler will do. So rather than do that, what I've actually done is a sort of crude loop here around a bunch of no operation commands, which will simulate a short pause, and hopefully that way, if the user is actually only wanting to type a single letter, that will have a bit of a debouncing effect, so to speak, and avoid reading in other key presses that were actually all the same key press. Now the clear screen command is here, and I've actually tagged in a few extra commands that are worth having. So first of all, here we're clearing the screen. Now on the SamCoupe, it's quite like the Spectrum in the default functionality, that it has a big top screen and a thin little bottom screen for data entry. So we set A to 0 to tell it to clear both of those screens, and then we're setting the mode, and we're using screen mode 0, which in the basic documentation is actually called screen mode 1 and is effectively the same as a Spectrum screen. And then next we're opening the channel that we're writing to, and we're writing to the channel FE, which is known as channel S, which is the upper screen. And here we've got a locate command. Now on the SamCoupe, we can achieve a locate just by writing to these two memory locations here, our H and L value, and that will do the job for us. And then GetCursorPos would be quite easy. We would you would think we would just read back from these memory locations again, but actually I did come across a little gotcha here. It seems when you do a new line command, the cursor, while it appears at the far left, which would be cursor position 0, it actually seems to default to cursor position FE, which I assume is some kind of internal I've been relocated but I've not printed yet kind of notation. But so just to avoid that and any other possible confusion, I'm checking for any value above F0 and setting them all to 0, so that and this will now give us the values we're expecting when the cursor is at the far left hand side of the screen. So that's not too bad, but a little bit odd there. So new line on the SamCoupe is just the same as the Spectrum. So we just load it, we just send character 13 to the screen, and that will do everything we need. So here's our print string command. Very simple. We just use the print char command over and over again. So that's about as simple as we can get. And then just one final thing. On the initialization routine, we've disabled the scroll prompt, which will appear when we get to the bottom of the screen. But I would say pretty simple for the SamCoupe here. And as you can see, we haven't really had to define a lot here to get all of the previous examples working okay. And this is the beauty of using these kind of functions that we've written ourselves, and we've kept as simple as we can, because this allows us now, any new system we come across, as long as we can create these few commands and make them work in the same way as the other ones do, all of our code will now work perfectly automatically with this new system. So that's kind of the benefit of writing our own code and trying to keep everything as simple as we can, and everything working in a common way. So there we go. So there's the SamCoupe functions. So as we mentioned, we've got the definitions for the screen and the key characters here. And on the Enterprise as well. Now the Enterprise screen is 40 characters wide and 25 tall. So again, we're using those definitions. And a rather odd character for backspace there, but never mind. The Ti-83 is our smaller screen with just 16 characters wide and 8 high. So I'm sure that's going to cause us some trouble if we try to make all our programs work on that. The SamCoupe in the screen mode we're using here is the same as the Spectrum again. So, and here's our definitions for the Enter key and the backspace key. ZX Spectrum as well, 32 characters wide, 24 tall, which seems to be quite a common thing. The vast majority of these 8-bits seem to be 256 pixels wide and 192 tall, or thereabouts. The MSX has some slightly taller ones, but so there we go. And then here's the MSX again, 32 characters wide, 24 tall. It does actually have a 40 character wide screen mode as well, where the characters are narrower, but we're not using that for now. We're sort of standardizing on that 32 wide on most of the systems here. So there we go. That's actually all I wanted to cover today. We'll be using these next week, these new functions, to create a character reading routine, and we're going to actually read in strings from the user, and we're going to be able to support backspace as well to delete characters that the user has entered, and that will allow us to take in lines of text from the user, and then we'll be able to do other interesting things with them later. As well, next week we're going to have an addition to the monitor. We're going to be able to show areas of memory on the system now as well, so that we can do better debugging of our system for when we're developing new things and testing things. Okay, I hope you've enjoyed today's lesson. Please like and subscribe to my channel if you want to see more, because we'll be going into far more detail than we have today. It was really just a picking up the details lesson this week, because I needed those extra functions for the more interesting things I'm going to be doing in the future. I'll be covering the SamCoupe along with the Enterprise and all the other main systems as we go down this tutorial series as much as I can. The only thing that may be limited on the SamCoupe is when we're doing the music with Arcos Tracker, because the SamCoupe doesn't have an AY sound chip, so unless I can find a way of emulating one, we won't be able to cover the music on that. But everything else, I'm pretty confident we'll be able to cover the SamCoupe in the same way as all the other systems. Thanks for watching today. Goodbye.